there is that chance of the uh, device conducting again, but after some time, it can fully block any forward voltage that is applied to it. But to ensure that does not happen, we normally reverse the terminal. So this is the switching characteristic of a thyristor. We are saying initially, the way it is with the main supply only, we need to bring some current through the gate to ignite it. And so the moment we are injecting current or electrons within that region, we are able to reduce the depletion layer or the potential difference that was in that one reversed junction. So it reduces as the current builds. So it will reach a point where it will ignite fully. So it has started, and after that time, it switches on. So this is the switching on time, the time to switch on a thyristor using this IG current. So it will continue conducting through that flow of a lot of current with less voltage. But if we need to switch it off, we reduce the IA or the anode current to zero. But we are saying the moment you reduce it to zero, because of the electrons and the holes near the junction, it switches off, but it will start conducting again in the reverse because of the few combination of electrons and holes near the junction. And then after some point, when we deplete those few electrons, leakage current reduces up to another point T4. But we have another system that will take more time. This is because of the forward voltage that can happen. So the T off can be prolonged. So we'll see what is T4, T5, and T6 that is turning off. But mostly you can see the thyristor is not conducting at T4 and also at T6. But the moment we apply another voltage after the blocking time of the thyristor, we can start again having conduction happening. Yeah. So the device switches on very quickly. The turn on time T on is typically between the range of 1 to 3 microseconds. And typically the width of the gate pass, whatever we were able to apply, is between 10 to 50 microseconds, and its amplitude is, so you can maybe ignite with a small current of maybe 20 up to 200 milliampere depending on the size of the thyristor. So if the current through the thyristor is required to be switched off at desired instant, maybe two, we need, at this point you realize you need to switch it off. It is momentarily reverse biased by making the cathode positive with respect to anode. So the moment you do that, you have to reverse junctions, and so the current reduces immediately, starts reducing. For this forced commutation, a commutation circuit is also commutation is required. Yeah, because of that, we say that effect of the forward voltage. So we need the commutation circuit to be able to block that forward voltage and ensure that the thyristor will not turn on when your aim was to turn it off. So if the device is reverse biased, its current falls, becomes zero at T3, then reverses and becomes zero again at T4. So it starts slightly for a small span of time, it conducts in the reverse direction because of that reverse current or the leakage current, and mostly it's the just interaction of the electrons trying to fill the holes that are just immediate, and then the depletion layer widens. At instant T5, now before at the instance between T3 and T4, the device has not fully gained the blocking capability, and it is at that point that if you put some voltage, it will start conducting. But at instant T5, the device has gained its full blocking, capable of blocking a forward voltage. So the time interval from T3 to T5 is known as turn of time, and that is the key. That is after that period that you can be sure that you are safe to do any operation. Even if you apply the forward voltage, it will not conduct. However, if a forward voltage appears at instant T6, the time interval T3 to T6 is known as circuit turn-off time. So if a forward voltage appears much later and the resistor is able to conduct again, we call it circuit turn-off time. But somehow this will be within the same region. It's as if you are starting again the thyristor. So in practical application, the turn-off TQ provided by the thyristor or silicon control rectifier, the circuit must be greater than the device turn-off time T off, that is between T3 and T4. Sorry, T3 to T5, where it has gained full blocking capability. So that is how we can be able to switch off the thyristor by ensuring that we turn it off, and also at what point do we inject the forward, at what point do it gain full blocking capability of the forward voltage. And to be sure and safe, we normally bring in as number circuit for the to ensure commutation happens and you're able to block any forward voltage that can happen. So this is the firing circuit where we are able to inject the current needed to ignite the thyristor, and then this is the commutation circuit, or the circuit to cross or to switch off the thyristor. So we have different types of thyristors, those which are normally fast switching, and also we have those which are slow switching. Yeah. Running time to before you have reversed the terminals and it takes more time before it switches off. We call them slow switching or phase control thyristors, but those which are able to turn off like within a small period of time, we call them fast switching or inverter type kind of thyristors. So if during turning on the thyristor, the voltage is still high and the current is still high, we could have experienced some losses. But in our situation during turning on, the voltage, when it turns on, the voltage is quite low and the current is high and the voltage is low. The voltage is high, current is low, and vice versa. So we started with when turning on, the voltage was high, and so it reduced when we were turning on, and the current increased. So before we turn it on, the current is quite low, and this ensures that the switching losses are very low. But if the current is high during the switching on, but we see one type of thyristor which has high current during turning on, then we experience a lot of losses within the system, which is not good for such for converters that are made with thyristors. So during thyristor turn off, if the reverse current is small, the turn off switching loss is low. Again, when we are switching off, the current also reduces, ensuring also the switching off losses are low. The low switching loss in thyristor is a significant advantage, particularly for high frequency application, and mostly where high frequency where we need to keep it on off on off on off. So it ensures all we have very low losses, or the efficiency is quite high. So this table here compares two kind of the thyristor, the fast switching and the slow switching, and the different capability. Mostly the rating are the same, but now some areas will have differences. The ratings are the same, but one is the slow switching and the other one is the fast switching device. So within your own time, maybe you can check that. So again, for thyristors, we need to protect them on two major issues. Mostly is the change in current over time, because if the current in the thyristor rises at too high rate or a short high amount of current passing through the system within a very short period of time, more so we can just say a short circuit, the device can be destroyed. So some inductance must be present or inserted in series with the thyristor. When we talk about inductance, it kind of slows the process. So if we had maybe 100 amperes passing in 1 second, when we bring an inductance to the system, we can have still the 100 amperes passing maybe now with 10 seconds. It's as if we store and then release in bits. In uh, we are able to prolong that time, and so the device operates within the same amount of current. So some and mostly it's put in a series with the device or with the thyristor, so that the change in current over time is below the safe limit specified by the manufacturer of each of the. For this can take up to 100 amperes and 110. If we exceed that and more so within a short period of time, we get to destroy it. Again, we talked about the forward voltage. If you apply it when you are switching it off, remember it can turn on, and so changing voltage over changing time, it may lead to improper operation of the circuit, and so we normally bring in a number circuit where some of these uh, power or voltage or current is stored rather than going to ignite again the circuit. So we introduce a number circuit, which is normally used to limit the voltage over time of the applied forward voltage. You can be asked to explain how the operation over the working principle over the thyristor using the Fouriers, and also explain the voltage ampere characteristic of a thyristor, detailed explanation, and how is the thyristor different from a transistor. Would you also be able to compare a transistor and a thyristor? The switching, what is forced commutation and what is natural commutation. So we have different types of thyristors. We have triac. The triac, we have two of thyristors that are connected in inverse. Yeah, in inverse what? Inverse parallel. Here they are. We have two of them. They are parallel, but they are still connected. So it has its own advantage that either way, we can either ignite it with a positive gate current or a negative pulse. For the one we are studying, we can only ignite it with a positive pulse. But now for this one, the moment we connect them in inverse parallel, we can either ignite it with a positive pulse, gate pulse, or positive gate current. And also, we can fire it with a negative gate current. So yeah, they are just two silicon controlled rectified silicon controlled rectifier or thyristor connected in inverse parallel. When terminal T1 is positive with respect to T2 and the device is fired by a positive gate current, it turns on. When T1 is positive with respect to T1 is positive with respect to T2, then we inject a positive gate pulse, the device switches on. And also when T2 is positive with respect to T1 and the device again is fired with a negative gate current, the device also will switch on. So mostly this kind of connection is applied in low power application like juice makers, blenders, yeah, such as those electronics, sorry. So it is economical and easy to control compared to two thyristors connected in anti-parallel. So the aim is to connect them in inverse parallel. However, a track has a lower change in voltage over change in time capability and a longer turn of time. So that is the disadvantage when you compare with just connecting to thyristors. Also, it is not available in high power applications, high power rating applications. Then again, we have the GTO, the gate turn off, the turn on thyristor. Which can be turned on by a single pulse of positive gate current, like the thyristor. But in addition, for this one now, the advantage is that the thyristor, we said when we ignite it, the gate current has no control. But for this one, it's made in such a way that a positive pulse will switch it on, and then a negative pulse will switch it off. So we can control it from the gate, both switching on and switching off. So this is the track, the volt ampere of a track. Then this is the GTO, where we can ignite it with a positive pulse, and also we can switch it on with a positive pulse and switch it off with a negative pulse. So that is the advantage of a GTO. So the symbol of the GTO and the symbol and the switching characteristics are shown here. The turn-on process is the same as that of the thyristor. The turn-off characteristics are somewhat different. When a negative voltage is applied across the gate and the cathode, the gate current Ig rises. When the gate current reaches its maximum value Ig3, the anode current begins to fall. So we are saying when a negative pulse is applied across the gate and it reaches its maximum, that's when the anode current will begin to fall. And we said whenever it begins to fall and we get to reach below the holding current, the device switches off. So we apply for using the GTO, we are just apply a negative pulse, and when it reaches the maximum that can be held by the thyristor, the anode current now starts reducing, and the system goes to switches off. The moment the anode current is reducing, the voltage across the device begins to fall, or the potential difference within the junctions begins to increase. And so at some point the depletion layer will be very big with no flow of current, and therefore the device will turn off. Therefore, the anode current changes slowly. This portion of the anode current is known as the tail current. So the ratio of the anode current and the maximum current required in the gate, the negative gate pass of the anode to the maximum negative gate current required to turn off is quite low. So if we were to compare the two, the anode current and the gate current required to switch it off, it's quite low. So we don't need a lot of current to switch it off. Typically 3 and 5. So for example, GTO that is of 2500 volts and 1000 amperes, it requires just a peak negative current of 250 to switch it off. So note that during turn off of both the voltage and current are quite high. During turn off, this off period, both the current, we still have a good amount of current and also a good amount of voltage. They are high, and so we can say the losses of a GTO are quite high. So that is one of the disadvantages when you compare it with the thyristor. And so mostly its application is for systems that are below 1 kilohertz, because if we put it in systems that are high hertz, it means or high power, we will have a lot of or high losses within the system. So the power losses in the gate drive circuit are also somewhat high than those of the thyristors. However, since no commutation circuits are required, the overall efficiency of the converter is improved. So we can say no commutation. For the thyristor, we were bringing commutation circuit, number circuit to enable it to switch off. So it's as if we are trying to say this has the disadvantage of high losses, but again, if we were to look for the cost, we don't have this number circuit, so the efficiency remains compared to those or to the efficiency of the Arista. Also, the GTO has no reverse voltage blocking capability. Remember the forward voltage that we are talking about, and so we normally bring in a diode to ensure it has that capability. So we normally include diode and number circuit to ensure it has a reverse blocking capability. Therefore, an inverse diode must be used if there is a possibility that appreciable reverse voltage may appear across the device. Yeah, I don't think there's something else. Although GTOs and the ERISA became available almost the same time, GTOs did not receive much attention as the ERISAs, and mostly you find the ERISA are more in the market when compared to the GTOs. So mostly people preferred the Thyristors compared to the GTOs. So that is all about the Thyristors. you. At what point did I go missing? Okay, thank you. So if you are done with GTO, we look at the rectifiers. Where when you say control rectifiers, for instance, when you are talking about the thyristors, we are able to control at what point do we want to ignite it, because we have the ability to inject the gate current. But for diodes, the moment we just bring the P and N material together, and we connect them in forward bias, it just starts conducting. But for the thyristor, we still have to add the gate current, and we can choose at what time or within the wave we want it to ignite when the voltage, when we have applied quite a high amount of voltage, or at what point. So when you are drawing voltage and current, we normally use this sinusoidal wave. We say it is alternating current. So, or when it is AC, it normally alternates between the positive and the negative. So for a diode, if we connect it with forward biased way, such as the negative terminal is connected to the negative material on the N material, and so on, it will, and it is one diode in a circuit, it normally allows the one that favors it, whichever wave is forward biased to it, it will allow it to pass, but it will block the other part that is reverse bias kind of. So it allows only in one direction. So if it is connected to allow the positive, it will block the negative side of the sinusoidal wave. So for diodes, we don't have control, so it will just allow the whole of that positive part to pass. But for diodes, we can decide at what point are we igniting. Do we need the whole positive part of it, of that wave, or we can ignite it at a certain angle, or at what point can we apply the current at the gate. So that is the difference between the thyristor and the diode. And so from there, rectifiers that are made from thyristors, we can say they are controlled rectifiers, but those which are made of only diode, we can say they are uncontrolled rectifiers. But we see we also have semi-converters where we have both diodes and thyristors within a circuit. So from there, we start with single phase circuits where we only have one wave, but we normally have the three-phase circuits where we have three of these waves with a difference of 60. They are 120 degrees electrically separated. So for this is a simple source, the single of the diode, and then 60. So we only have resistance within the system. So this wave normally moves from, or we can say it is in the range of 0 to omega, or this is omega t. The wave is called omega t, where it ranges from 0 to pi, or the difference, or the, what is it called? This distance of every half is 0 to pi. Then this is pi, another pi. So if you add them, it's 2 pi, 2 pi, 3 pi. And so we inject this kind of a wave to allow it to pass through the diode. So when it is positive, it to be allowed to pass through the diode. When it is negative, it is blocked by the diode. So only the positive passes through the diode. The negative part is blocked by the diode, and so all the positive parts will be allowed by the diode to pass. But if you connected it the other way, if this is connected in the opposite direction, we have this facing the other side, it will allow the negative to pass and block the positive parts. So the voltage output, this is the output, the voltage that it gets to reach the load or the machine that you have connected in this part. It will receive this voltage. Then we know current is equals to V over R. So it is voltage divided by the resistance within that system. And yeah, so it is the amplitude of the current is quite low than that of the voltage because of dividing voltage with resistance. But still we have current rising from 0 and falls to 0, back to 0 at pi. So for this one, let us do this calculation again. For this voltage, we normally say it is the root mean square of voltage. So it's normally root 2. If you are to calculate to get the value, we normally say it's root 2 Vp, or Vp is the amplitude of this voltage, and then sine omega t. It is sinusoidal, so we normally still give it the sine omega t. So we normally say like whatever we are tapping from the socket is normally called the root mean square voltage. So it's normally the root 2, the high multiplied by the highest point of that voltage, and then it is sinusoidal wave. So how do we get to calculate the voltage that gets to the device? So the V naught will be 1 over pi, 1 over 2 pi. What is the whole cycle? The complete cycle is from 0 to 2 pi. So it's 1 over 2 pi. But what is getting to the device is only between 0 to pi, because the other part has been filtered. The other part of the complete cycle has been blocked by the diode. So the range we integrate from the range of 0 to pi of the output voltage. Then you substitute this output voltage with this, and you put root 2 Vp sine omega t d omega t. Then you integrate. When you remove the constants outside, so root 2 Vp are constants. Then you integrate sine omega t. When you integrate sine omega t, what do you get? When you integrate sine x, do you remember when you integrate sine x, what do you get? Yeah, thank you. You get negative cos x. So when you get negative cos x, you substitute. So I don't have a writing part for this, but maybe I did just done some few calculation here. I hope you can see this. So this is you remove the constants outside, root 2 Vp over 2 pi, then you have sine omega t. So if you integrate sine omega t, you have negative cos omega t in the range of pi to 0. Then you substitute the range from the highest, so it will be negative cos. You put a pi, then minus. You subtract the raw value minus, then negative cos 0. So cos pi is -1, and then negative and negative becomes positive. Cos 0 again is 1. So this will be 1 plus 1. You have 2. Then the 2 will cancel with the other 2, and the final value will be √2 Vp pi, and that is what we had on the other side. So during the calculation, mostly this is expected to be shown when doing those calculations on your work. So that is when we have a single diode within a system. And then, yeah, that is the diode. But then we can have a thyristor. And now a thyristor, we are not just igniting from 0. It is the same operation, but now we are not igniting from 0. We are igniting at our chosen point. It can be any point. Now we give it alpha instead of 0. And so for this one, the result will be 1 plus cos alpha. But before we go there, kindly, maybe within your own time, before we go to the thyristor, or maybe you can also check for the thyristor. It is the same way we are describing, but now we are igniting at not at 0, but our chosen point. But you can still say, what if alpha is 0, or what if alpha is 60? So we can define, do you want to ignite the system at 0 degrees, or at 90 degrees, or at 180? What is our alpha? So we can either decide to leave the alpha within the calculation, but you can be told that alpha is 60. So we find cos 60 and complete the calculation. So before we go there, maybe you will find your own time and consider now we have two diodes. Both are for, or also on this side, the what? Both the positive and the negative get to reach the load. So you will draw the circuit, the same circuit, but now with two forward biased diodes that allow both the positive and the reverse to pass, and see how will this wave look like, and how will this calculation look like. I hope that is good. So you can do it on a written, whatever, full scope. You draw, maybe I have to summarize it. You draw, and then I'll guide you on how to share it. So you do on a handwritten, maybe you can scan that the full scope, and then I will create a Google form or a Google whatever where you can upload them. I hope you are good. But I will give this instruction in a better detailed manner, and where to submit the scan of the PDFs. So are we together? Hello. Okay, so I beg to stop there. Then in the next during our next class we now go into detail on the rectifiers and then on inverters. So we have 4 major converters: the rectifier, which we have already started, inverter, then the other 3. So we'll see how to cover them soon. Then we go to mechatronics. So enjoy the rest of your evening.